chapter for this opportunity to present the cutting-edge work to correct or to solve the problem of stable isotope data that has noise. Because that was my question in 2012 when I was at Texas A&M, telling them that, hey, I see wiggles inside this curve. And they said, no, when you have diagenesis in the oxygen curve, just trash it. But I told them it can be retrieved, but I was not able at that time, My level of maths and statistics and the focus was not there yet, but from my mathematical background, I was saying like, oh, it can be. And after now 10 years, 12 to 22, it's done. And we're presenting it now. And the method is called Cyrenaica method. And Cyrenaica method is data science analysis and applications in geology to clean and correct patterns of oxygen and carbon stable isotope data. And here, I would like to thank my team and thank Dr. Hatem al-Barghati, PhD in math physics, who reviewed our math, and Dr. Abdul Basit Amrouni, who reviewed the PhD in statistics, who reviewed the statistical methods. So 2 PhDs from the US reviewed the work besides the geology people, the geology. Okay, and this is my segmentology team here. And the data is the same data that we use it for we focused on A1 section that has 74 meters, that has everything that we need. Stable, carbon stable isotope and oxygen stable isotope values from 148 samples that sampled every half a meter. And we have still the XRF data, the thin sections data. And the most important outcomes here, the carbon told us like almost the whole Miocene is preserved, and the Cyrenaica method that the abbreviation with CM is a new method and carries discovery that isotope data, especially oxygen, can be altered due to diagenesis, but will never reset. So we can separate the noise from the original data, the clean signal. In a way, very comparable to the clean data that we can get from the fossil method. So we use it here in this data, whole rock method. And the Cyrenaica method, CM, applies mathematical and statistical data science analysis in geology to clean and correct the patterns. I'm focusing on the patterns, of the oxygen stable isotope. Plus, this Cyrenaica method, this new method, will give the stable isotope studies that based on whole rock an advantage over the data coming from the fossil-based isotope study, because this will give you 2 things. The noise, which is basically the diagenesis or the exogenous factors, as they call them in statistics, plus the pure signature, or a signature very close to the pure signature, like comparable to the pure signature. So now on the whole rock studies will have this advantage over the fossil studies because they're like quicker and faster. And let's go to the study area. The study area is Cyrenaica. Here, this is A1 section at the outcrops. And this is Cyrenaica region, and we have our section started from the stratigraphic section, from red algae to bioclastics to oolitic, and then microbial, and then the selenitic gypsum, green shale, and sandstone. This is the typical shallowing upward sequence in CERN. Okay, let's go. And methods and data, we have field work and observations, and we did 29 detailed sections, and we chose one section, which is A1, to do the lab work, which is the petrography, XRF, stable isotope, oxygen and carbon, besides the sequence stratigraphic interpretations. And we did analysis for thin sections to identify the components of our rock, especially texture and cements, diagenesis, porosity, and 148 samples we did also trace and common elements. Okay. Methods and data. So we did, as we said, whole rock stable isotope samples. We chose A1 as a complete, has complete set of data. And we got the oxygen and the carbon isotopic signatures or values, okay? And, at Texas A&M facilities, and this is the precision for oxygen and carbon, 0.04 and 0.08 for carbon, 0.04 per mel, and 0.08 per mel for oxygen, respectively. And and then the plotting of oxygen and carbon isotope values, individually creating their own profiles. And as we said, the data or maximum flooding surface was at the Miocene, coincides with high gamma ray and positive incursion of carbon, which was the Monterey event. And then the oxygen tied with the sequence stratigraphic analysis and the gamma ray profiles to get our sequence stratigraphic framework set up. And then here, the Cyrenaica method, as we said, is a data science method just to clean and correct patterns. And the Cyrenaica method algorithms include 3 steps, basically. Data pre-processing. This is before you start. You have to pre-process your data, and then you get the first derivative of your data, and then integrate your data values, either oxygen values or carbon values. You do them one by one. This is the sequence stratigraphic framework of the Cyrenaica, as explained earlier, but I have to repeat myself here to just this separate presentation. As we like from bottom to top, we see blue color and beige color, light and dark beige. The blue color bioplastic, the beige color is red algae. As you go up, you see these 2 colors starting like shrinking and disappearing and giving up to the yellow color, which is oolitic facies. So the subtidal facies will give the way up to oolitic facies, ramp crest, and then the ramp crest will will change into evaporite, the red color, and the orange color microbial facies as you go up vertically. Laterally, you see some siliciclastic facies, the black and green here. This is shale and sandstone, green shale and sandstone. And this green shale has so high gamma ray, like my machine was screaming in the field. The first time to hear it, it's above the scale, and it scared me that day. And this is, as we said, this is A1 here. It's in the middle of the study area. To the left side north, which is Jabal Khadar. To the right side is south. And this section is exactly at the place, very famous place. It's called Ilgara and Mayita in Suluk, uphill there. As you go through the road of Suluk, Labyar's road. That's a road cut. Let's move on. So the same section again. That for A1, this is on the left side. The field work, the sequence stratigraphic interpretation, the cycles. These the 2 second order super sequences, and here the third order sequences. And then here we have the calcium weight percent curve. It has 3 depletion zones, A1, A2, A3. And here the carbon isotope, not corrected. This is the running average, 3 points running average. Curve, we did it at that time because we didn't know about this method that we're discussing today and explain, and shows 3 intervals of carbon positive excursion, the middle Miocene called Monterey, and here the porosity that came from the topographic section work. It has P1, P2, P3, those porosity increase zones. And again, the porosity facies, these oolitic facies has biomolded porosity, red algae has biomolded porosity too. Omolded, and here fenestral porosity in microbial facies, and here fracture porosity This is oyster shell, bioclastic species, and here growth framework, growth porosity in a bryozoan, and here the biomodic porosity in forams, which is Borellus. Now, the method. This is the pith of the bone. The method. The method, Cyrenaica method algorithms, as we said, there are three main steps: data preprocessing, first derivative, integration, and then the final data set. So here, this is the first step, which is data preprocessing. So if you look at the black line, this is the original data, altered data. The first thing we did, we just rotated data to the x-axis. So the x-axis is our time interval, and the vertical axis is the values. And here I'm giving example for the carbon because it's easier to see the changes. And I'll apply the same thing on the oxygen, and I show you the results of oxygen too. So start with carbon because it's easier, has less diagenesis than the oxygen. Okay, so what we did, this black curve, we just rotated up, gave us this red curve. Okay, this is the first one, carbon isotope, and then the red curve is the rotated carbon. And then we did range limit. Basically, we divided this values of the rotated curve by specific value. We deduced it from the data, and gave us this reduced, amplitude species to avoid, in our calculations, something they call it heteroscedasticity in statistics. That's when your data spreads in one side, especially with increasing values. So what happened to my data? So this is my data here in the histograms. If you look at the black here, related to the black original data. And then when you rotate it, look at the data, it's become normal distribution. Statisticians, they love this distribution. And then when we did the limitation of the range, it's still the same normal distribution, but if you look at the x-axis, you'll find the values of the range decrease. The minimum becomes minus 1.16, and the maximum becomes 3.5. While it was going to minus 9 up to 5 positive. So it was wide range, and this thing just limited the range, shrink it, and make my data normally distributed with this little trick, which is rotation, data rotation. Okay, now do the first derivative. So the rotated, the range limited carbon data after rotation, you get the rate of change from that. And then we plotted the rate of change here. Okay, this is the first derivative of my data. We still have spikes. That's the ones that we need to get rid of. And by the way, these spikes coincide with the package's boundaries, so they are surfaces, important geological surfaces. Then what happened to the rate of change? What happened to the data? The data comes range from minus 3 to 3 positive. In most, as we said, the total of my data 45 values. This is for carbon, and most of my data concentrate around this there. So almost like almost concentrated almost around 0. Okay. So we need to transform this data, and all this work we do to get the actual rate of change in the values of my carbon stable isotope. Because the original data, it has two things. It has, if you look at the black, it has diagenesis plus noise, noise plus the clean value. So diagenesis made the alteration and gave me deformed rates. So I'm cleaning up here my data to get the actual rate and get rid of all these jumps and spikes that you see here. Okay, so the transformation, after transforming the data, we get this. This is the transformed carbon-13 data. And there is an equation for this transformation. And then after you transform and integrate, you will get the blue curve that shows you two things: direction and rate of change. This blue curve, it will come with some trend, so you need to just do axis rotation again. When you do axis rotation, will to the x-axis, will give you the red curve. So axis rotation is always important. You have to do it, otherwise your final curve will be twisted. I did this work without axis rotation, and the final results twisted. But if I did, when I did the axis rotations in these steps, the final results was impressive. Okay, now the final signal. The final signal shows, this is the original, which shows like inverted triangles, dots, but the final signal is the green curve here. So we got rid of all the spikes, and we have now a smooth signal showing me the ups and downs of the carbon isotope. As you go from 0 to 80, you are going to like from old to young. So this is the middle Miocene here, and this is the late Miocene here, and back down here earlier, okay, in age. Now, we have three things: altered carbon, altered curve, this is the original curve, and the clean signal, okay? And we are comparing it with the Zagos. Immediately we can spot here, you see the middle Miocene event? We immediately can spot it, but in the original data here, it's deformed and distorted, and it's hard to see. It's really hard to see, unless you know what you're doing. But from this, immediately you can compare with the Zagos curve. This is the Zagos that came from fossil-based method, and this is our clean data that based on oil. Okay, we did the same thing for the oxygen. This is my distorted oxygen at the top here. You see the spikes and jumps everywhere, and the breaks in the curves. And this is the clean oxygen. We did the same steps that we did with the carbon. We got this. And look at the events. You know, here, if you look at this, you know, this is from early Miocene all the way to the late Miocene. If you look here, like from like middle to late, we have a lot of evaporites, and we have heavy oxygen. So here, this is local event to Cyrenaica. We have evaporation. You know, evaporation and glaciation, they give you the same signal, like heavy oxygen. And here we have this really heavy oxygen signal in the Cyrenaica. It's very local. So I know my lithology, and I was expecting this. But if you look at the original data, it does the opposite, gives you negative, like completely different. We need it enrich it. And you can see the patterns and the early middle Miocene changes in the oxygen values. And it's really like impressive that you can clean up, you know, data that everybody advising like trash it, it's useless, using Cyrenaica method to clean it and process it and get like really comparable results to the fossil-based. And by the way, if you look at the carbon, because it has minimum diagenesis, it shows like way better signal than the oxygen, you know. And then after doing this is Zagos, by the way, the blue one Zagos, and the middle one is the Cyrenaica Miocene. So this is Zagos Miocene. And also, if you look here at the curves, you find like a great correlation until like here, and then this section telling us the Miocene that we thought is Miocene, it's older than Miocene in the bottom of my section. We have older age, but I'm not going to say it. I don't want to have problems with paleontologists, but my stabilizer is telling me there is something. Go next. Now, the moment of the truth. So we did the cross plot. So the diamond, the blue diamond, that's everywhere. We see it from here all the way to down. So it goes negative to the x-axis, which is the oxygen stable isotope, and going down the y-axis, which is the carbon isotope. So we call it inverted J. Inverted J means there's huge diagenesis. Okay, this is our data before processing. But after processing, we have three. Even the Cyrenaica method has three ways to apply. CM1, CM2, CM3. Just in the presentation now, I showed you just the general method, but there are three inside it, more details. We find out CM1 is the best, red squares, and the second is the triangles. But the third method, if you look at these inverted triangles, they have distortion in the x-axis. They go far away. But the red and the green, red squares and green triangles, they are clustered. But the red have better cluster on the x-axis than the greens. So we chose method one, and that's what I presented in the explanation. Method one that shows really good results when you do, and good cluster when you do, and these values very comparable to the fossil-based results for oxygen and carbon stable isotopes. It's really impressive. I was impressed. And now, can we do better? Yes. There is Barga method, BM, can do better than Cyrenaica method. But what I presented here, just Cyrenaica method. I show you the results. So here, the carbon isotope and the upper table, and the lower table, oxygen isotope. If we look at the carbon isotope, these my original values that from whole rock has diagenesis. When we use the Cyrenaica method, we got this standard deviation 1, maximum value 2, minimum value -1. But when we do Barga method, look at the standard deviation 0.6, equal to Zappos. Like variations almost none. So this second method like kills any variations, like gives you the same original signal as if you are doing fossil-based method. And you have the maximum and minimum, but the range here, look here, range 3.75. The Cyrenaica give you 4.1, but the Barga method will give you 2.7. The same thing for the oxygen. If you compare the values, the standard deviation of Cyrenaica method, CM 0.8, for Barga method 0.5, it's comparable to Zappos. If you look at the range, which is the difference between max and minimum, Cyrenaica 4, Barga method 2, like cut by half, and Zappos is 2.85. So Barga method is way closer to the real values. But that will be a future presentation or future work. But now just introducing people to the simplest one, in my opinion, simpler, Cyrenaica method. And results and conclusions. So the good news is Cyrenaica method, here is a new discovery. Stable isotopes, data never reset, can be retrieved from diagenesis. If there's diagenesis, we can split diagenesis signature from original signature. And Cyrenaica method applies, mathematical and statistical data science analysis in geology to clean and correct patterns of oxygen and carbon isotope data, as you saw earlier in the slides. And first time applied in Cyrenaica, in the Miocene of the Northeast. The Cyrenaica method will give the stable isotope studies that are based on the whole rock the advantage over the stable isotope studies that based on the fossil rock, because you have two things: signature of clean data and signature of the noise. Then this noise is diagenesis. So if we use this diagenesis and see the spots where they have the most diagenesis, later when we do petrographic study, we can focus on these regions that have higher alteration and deformation if we're looking for porosity or segmentation. So that will help us even in our research and telling us where to find the the packages or the zones that have the highest deformation and diagenesis. So the outcome of the Cyrenaica method or data processed with this method will give you more accurate and narrower range of the stable isotope values, where oxygen, data ranges from -1.7 to 2.2 at the carbon -0.18 to 2.3. When we apply to Cyrenaica, we reduce the values. And this range, of the cleaned processed Cyrenaica Miocene isotope whole rock data are very comparable to the stable isotope data came from fossil-based, like Zakos. Zakos data, the oxygen is 1.1 to 3.7, and our oxygen is -1.7 to 2.2. And the carbon for Zakos is -1.3 to 2.4, and we almost hit it in the zone here, -0.18 to 2.3. Maybe we're better here in the upper end of the carbon per mil. And the same as we said, the carbon told us like the whole Miocene, almost the whole Miocene section is preserved, early, middle, late, because they use it. Before the study was everyone was thinking it's just middle and late. Well, now, no, it's early, middle, late. And it has Cyrenaica Miocene has six cycles of third order sequences, and these arrange it in two super sequences, and they all form a Rajma group of the Cyrenaica Miocene. And as we know, the Cyrenaica Miocene by now is ramp system, has oolitic grainstone as a crest ramp facies, and it has subtidal facies, which is red algae and bioclastics, and it has supratidal facies, mainly microbial and evaporites with some cystoclastic influx. And by this, I'm done. Thank you very much, and I appreciate your attendance.
Thank you very much, Dr. Khalid. I think this opens up a wide range